All right, welcome to the deep dive. Today we're going to be tackling René Descartes and his work La Géométrie from 1637. I think a lot of people hear La Géométrie and they're like, math, equations, shapes, all that stuff. But, and I think this is particularly interesting for a philosopher, it's not just about crunching numbers, right? It's really about the very essence of what these geometrical things are and how this whole world of algebra, which seems so abstract, connects to this visual, intuitive world of geometry. It's like we're digging down into the foundations of how we even think about math.
Absolutely. La Géométrie wasn't just like a how-to guide for solving geometry problems. I mean, at its heart, you have Descartes trying to create this geometrical calculus, this whole system for using algebra as a tool to really understand geometry. Like, how do you actually construct a curve, and how does that relate to its equation? And can you even categorize curves based on the complexity of their equations, the degree of the equation? What's fascinating philosophically is that he's trying to find this unified framework, some kind of set of principles to make sense of all this mathematical stuff.
Okay, so before we jump into the nuts and bolts, I think it's helpful to set the stage. To really appreciate what Descartes is doing, we got to travel back in time a bit to the early 17th century. Mathematicians back then were having this huge debate about what even counts as a legitimate geometrical proof, and also which curves are allowed in the game. It's are all curves created equal? And this debate got even more heated when Pappus of Alexandria's collection came back into the picture. Imagine Pappus laying down the law or maybe creating a difficulty rating system for how to tackle geometry problems.
Exactly. Pappus comes along. He's like, all right, we've got three types of problems here: plane problems, solid problems, and line-like problems. Plane problems, those are the ones you can solve with just straight lines and circles, the classic Euclidean stuff. But then you've got these solid problems. Those require conic sections, ellipses, parabolas, hyperbolas, those more sophisticated curves. And then on top of that, you've got these line-like problems, which are, they're the ones that need even more complex curves, things like spirals and quadratraces. And, this classification system, while it's really insightful, it also kind of opened up a can of worms, philosophically speaking.
Yeah, totally. Pappus's work kind of created this fundamental ambiguity. Were these solid solutions with their ellipses and hyperbolas, and especially these line-like solutions with their even weirder curves, were they really geometrical in the strictest sense? It forced mathematicians to grapple with this really deep question. What makes something truly geometrical? What are the criteria for a mathematical object or a construction method to be considered legit in the world of geometry?
And that's where Descartes comes in, right? He walks into this kind of murky territory, and he's like, okay, here's my take on what counts as geometrical. And he's not just accepting those ancient classifications. He's trying to build a whole new foundation, and he's using the power of algebra to do it. So what we're going to do today is dive into Descartes' method. What are his rules for geometrical legitimacy? And ultimately, what does all this tell us about his philosophical ideas about what math is and how we know things in math?
All right, so let's start with this whole debate about constructing curves. Pappus, he gave us these categories: plane, solid, and line-like.
Yeah.
Based on the curves you need to solve the problem. Seems pretty straightforward at first glance, right?
Yeah, on the surface, sure. But as always with philosophy and math, the devil's in the details. Pappus himself didn't really make it clear whether using conics and these more elaborate curves was really kosher according to the super strict standards of classical geometry. Were they just convenient tools, or were they actually fundamental geometrical objects in their own right?
Right, exactly. Think about some of the classic problems, like bisecting an angle. That's pure plane geometry, the kind of stuff Euclid was all about, just lines and circles doing their thing. But then you've got these notorious problems like trisecting an angle or squaring the circle. Those were classified as line-like problems precisely because they seem to require these weirder curves like the spiral or the quadratrix. It's these curves were somehow beyond the basic starter kit.
And the way these curves were even conceived, described, is really interesting. You've got Archimedes, who talks about generating a spiral by combining this uniform circular motion with uniform linear motion along the rotating line. And Pappus himself gives this description of the quadratrix based on two line segments moving in this synchronized way. But these descriptions just felt different, more contrived than just intersecting lines and circles. They were breaking free from those classic straight edge and compass operations that had been the gold standard for so long.
And naturally, mathematicians started trying to find ways to legitimize these more complex curves. Clavius, he was really into quadratrix. He actually tried to come up with what he called a truly geometrical construction for it. like a way to plot the curve point by point using just a straight edge and compass. And he did this specifically to address Pappus's concerns about its geometrical status. He was basically trying to make the quadratrix acceptable for solving this big problem of squaring the circle.
So Clavius's approach was to create this discrete approximation of the quadratrix. He'd construct all these points and then connect the dots, essentially. And he argued that this point-wise construction was just as precise, if not more so, than the methods that relied on these simultaneous motions. Interestingly, he initially compared his point-wise construction to the way Apollonius constructed conic sections, as if to boost its geometrical credibility. But later on, he seemed to backpedal a bit, admitting that these curves were more accurate, but maybe not unequivocally geometrical in the strictest sense.
And then you've got Viet, who took this totally different, almost radical approach. He basically said, let's just assume we can solve this thing called the Neusis problem. Now, the Neusis problem is all about constructing a line that goes through a certain point and intersects two other lines at a specific distance. And by just saying, okay, let's pretend we can do that, Viet could then tackle things like trisecting an angle and finding mean proportionals without needing conic sections or any of those fancy curves. He was trying to redraw the boundaries of what was considered a valid geometrical operation.
Yeah, Viet was basically expanding the definition of a proper geometrical construction by introducing this new primitive, this new Mises thing. But, and this is a key philosophical point, he never actually showed how to construct the Neusis problem using just the classic tools. He just declared it legit. And then, to top it off, he argued that any curve that couldn't be constructed using his Neusis method, like the spiral and the quadratrix, well, those weren't truly geometrical in his book. So he created this new dividing line based on his own set of fundamental constructions.
So this is the world Descartes walks into. This whole debate about what even is geometrical is raging. And his early work shows him wrestling with these same fundamental questions. He went to school at La Flèche, where he probably encountered Clavius's work, his stuff on algebra, his edition of Euclid, with that pointwise quadratrix construction, even his practical geometry textbook. So Clavius was definitely an early influence.
Oh yeah, Clavius was definitely a big influence early on. But then comes this crucial moment. Descartes meets Isaac Beeckman in 1618. And they don't just talk about pure math, they're also into applying math to, understand the natural world. But even amidst all that, they're still debating the foundations of geometry and algebra, which really laid the groundwork for Descartes' later breakthroughs.
And it's around this time that we see Descartes' ambition taking shape. In this famous letter he wrote to Beeckman in 1619, he talks about this vision he has for a wholly new science that can solve all problems of quantity. He's already thinking about classifying geometrical problems based on the types of curves you need to solve them, kind of like Pappus did.
But, and this is philosophically important, Descartes is already being, picky. He says that curves generated by diverse motions, which he calls imaginary curves, those aren't truly geometrical. So even at this early stage, he's trying to set some strict standards for what can be considered legit geometry.
And that's where this really cool idea of his comes in. New types of compasses. He says that if you can generate a curve using one of these special compasses with a single continuous motion, then it's a bona fide geometrical curve.
Right.
He's basically saying we need to move beyond the limitations of just straight edge and compass constructions.
And we get a glimpse of these ideas in his Cogitationes Privatae, his private notebooks from around 1619, 1620. He describes this compass with all these hinged rulers and rods, and it's designed to generate this curve that can trisect an angle and maybe even divide it into more equal parts. The key point is that the specific angle you're trisecting doesn't affect how the curve is actually made. The mechanism is independent of the specific problem.
He also shows off his Mesolade compass in these early writings, which is specifically for constructing mean proportionals. And fun fact, this same compass pops up again later in La Géométrie in Book 3, which suggests it was a pretty important tool for him. And you can see that even at this early stage, he's fascinated by the relationship between geometrical constructions and how we represent numbers and do arithmetic.
Oh, yeah, for sure. You can see this in his Progymnasmata de Solidorum Elementis, which is from around 1623. He's really digging into how to represent arithmetic operations geometrically. And his letters to Beeckman in the late 1620s show that his algebra skills are getting seriously good. He's even figuring out how to construct the roots of cubic and quartic equations using conic sections. So even before La Géométrie comes out, he's putting together all these mathematical tools and philosophical ideas that will make his work so revolutionary.
So fast forward to 1637, and boom, La Géométrie hits the scene. And it seems like this guy, Golius, a Dutch mathematician, played a key role. He basically challenged Descartes to tackle this famous problem, the Pappus problem. Now, for the philosophy folks out there, the Pappus problem is what we call a locus problem. The solution isn't a single number or a line, it's a whole curve, all the points that meet certain conditions. Like, imagine you're trying to map out the path of a point that has to follow some strict rules.
Exactly. Unlike a lot of the geometry problems Descartes had been working on, the Pappus problem was all about actually constructing a curve. And in its general form, it's got a bunch of lines and angles in this constant ratio. The goal is to find the curve that's formed by all the points where the distances to those given lines have that specific ratio.
And Descartes had this huge breakthrough with it. By 1632, he's telling everyone that he's cracked the n-line Pappus problem, something the ancient Greeks never figured out. And he specifically says that algebra was the key. He even tells Mersenne that if anyone else solved it without using algebra, he wouldn't believe them. Talk about confidence in your method.
This Pappus problem victory seems to have really cemented Descartes' vision for geometry. As Henk Boss, the math historian, argues, it gave him this new, more structured understanding of the whole field, and it really reinforced his ideas about what geometry was all about and how you should do it. And La Geometrie is basically the embodiment of that vision. The Pappus problem isn't just some side note. It's central to how he lays out his geometrical calculus. It's in Book 1, where he explains his method of geometrical analysis, and then again in Book 2, where he does the synthesis, the geometrical demonstration, which relies on his famous distinction between geometric and mechanical curves.
Okay, so let's dive into Book 1. The title is, like problems the construction of which requires only straight lines and circles. Might sound kind of basic, but this is where Descartes lays out his revolutionary geometrical analysis, showing how you can systematically translate geometry problems into the language of algebra. It has some similarities to Viet's algebraic geometry, but with some really important innovations.
What Descartes does in Book 1 is genuinely groundbreaking, philosophically speaking. He gives you a geometrical interpretation for all those basic algebraic operations, even things like extracting roots. But the really clever part is that he treats these operations as being closed on line segments. Like traditionally, if you multiply two lengths, you might think of the result as an area, but for Descartes, it's another line segment. This might seem like a small thing, but it's huge. It lets him create equations where all the terms have the same dimension, which is essential for connecting algebra to geometry.
And he also adopts this new, much more efficient way of writing exponents, which makes his algebra so much cleaner and more powerful than what people were using before. This notation really strengthens the connection between the algebraic equations that describe curves and the actual geometrical properties of those curves.
So with this awesome algebraic toolkit, Descartes explains his method of analysis. The basic idea is to start by pretending the problem is already solved. Then you assign variables to all the lines, the ones you know and the ones you don't. And then you try to find equations that describe how all these variables are related. The goal is to get an equation that connects the unknowns to the knowns, and boom, you've solved the problem.
He gives you this nice, clear example of extending a line segment to show how this analysis works. You just set up the algebra based on what the problem tells you, and then solve for the unknown length. But this analytical approach is really powerful when you use it on indeterminate problems, those locus problems like the Pappus problem, where the solution is a whole curve, not just a single point.
Right. With those locus problems, Descartes says to think of the unknown lines as coordinates in a system. You pick some to be your variables, usually x and y, and then you figure out equations that connect those variables based on the conditions of the problem. And this is exactly what he does with the four-line Pappus problem in Book 1. He uses these oblique coordinates and the idea of similar triangles to get an algebraic expression that defines the locus of points that satisfy the given ratios, all in terms of x, y, and the constant z that's given in the problem.
And the result of all this algebraic analysis is super powerful. Descartes shows that for the general n-line Pappus problem, you can always reduce it down to a polynomial equation with two unknowns, x and y. This is huge because it means that you can, at least theoretically, construct the Pappus curve point by point. You just pick a value for x, solve the equation to get the corresponding y value, and you've got a point on the curve.
And what's really cool is what Descartes says about the degree of that polynomial equation. He claims that if you can get it down to a second-degree equation, then you can solve the problem geometrically using just a ruler and compass. Third or fourth degree, you need conic sections. Fifth or sixth degree, you need an even more complex curve, 1 degree higher than the conic sections. This is a bold statement. He's saying that algebra can not only solve geometry problems, but it can also tell you how complex those problems are.
So we get to the end of book 1, and we had this algebraic description of the solution to the Pappus problem. And we know how to construct it point by point. But for a philosopher, there's still this nagging question. Are these Pappus curves really geometrical in the purest sense? Can we construct them in a way that meets those strict standards of geometrical legitimacy? And that's the question Descartes tackles head-on in Book 2, which is called On the Nature of Curved Lines.
Book 2 starts with this famous and maybe a little bit controversial distinction that Descartes makes between geometric and mechanical curves. He's engaging with the language that the ancient Greek mathematicians used. He even says he's surprised they didn't do more to distinguish between these more complex curves, and he questions why they called them mechanical instead of geometrical.
He pushes back against this idea that the distinction comes down to the tools you use to construct them. After all, even to draw a straight line or a circle, you need tools,
Right.
a ruler and a compass. And he argues that just because you're using a more complicated tool doesn't mean you're sacrificing precision or geometrical validity. For Descartes, the real criterion is whether you can generate the curve using exactness of reasoning.
This is a huge philosophical shift. He's moving away from Clavius's focus on accuracy of construction and Viet's rejection of curves made with more elaborate instruments. For Descartes, what makes a geometric curve is whether it can be made by clear and distinct motions that we can completely understand and describe.
Then he lays down this important postulate. If two or more lines are moving in a defined and related way, their intersection can create other more complex curves. And to illustrate this, he brings back his Meslade compass, the one from his earlier work. He shows how the interconnected rulers in this compass can create a whole series of curves, each one more complex than the last. But he argues that the motions involved are just as clear and distinct as the simple rotation of a compass to draw a circle.
And he contrasts these geometric curves, which come from these nice clear motions, with mechanical curves like the spiral and the quadratrix. He says that to make those mechanical curves, you need two separate movements whose relation does not admit of exact determination. Specifically, the relationship between a straight line and a curved line. Like with the spiral, you've got this uniform linear motion along a rotating ray, and you've got the ray itself rotating uniformly. Descartes says that the ratio between the distance traveled along the ray, a straight line, and the angle of rotation, which is related to a curve, can't be precisely defined algebraically in a simple way.
So for Descartes, a curve is only geometric if it has a definite and precise relationship to a straight line, a relationship that can be captured in a single finite algebraic equation. That's his ultimate test. And then he goes on to create his algebraic classification system for these geometric curves based on the degree of their equations. Class 1, that's degree 2, and it includes circles and conic sections. Then you've got class 2, degree 3 or 4, class 3, degree 5 or 6, and so on.
And this brings us back to the Pappus problem. In Book 2, Descartes wants to show that all those curves that come from the n-line Pappus problem belong to these geometric classes, based on the degree of the equations he found in Book 1. For the 4-line Pappus problem, he proves that the equation is second degree, which means, according to his system, it's got to be a circle or a conic section, which are those class I geometric curves.
But this is where a philosopher who's really into rigor might start asking some tough questions. Because even though Descartes says that Pappus curves are geometric, based on his idea of constructing them with precise and exact motions, the connection between his algebraic analysis and this motion criterion isn't always super clear.
That's a great point. Even with the relatively simple 4-line Pappus problem, when Descartes wants to show that the solution is a conic section, he relies on those classic constructions from Apollonius, and as Hank Boz points out, those Apollonian constructions, which often involve, like, slicing a cone, they might not have been universally accepted back then as coming from perfectly clear and distinct motions in the way Descartes defined them.
And then, when Descartes gets to the 5-line Pappus problem in Book 2, he actually uses a pointwise construction to make the curve. This seems kind of odd, because he's so focused on continuous motion as a hallmark of a geometric curve.
He tries to explain this by saying that constructing a geometric Pappus curve, point by point, is fundamentally different from doing the same thing with a mechanical curve, like the spiral or quadratrix. He says that with a geometric curve, you can pick any point on the curve and find it what Boss calls a generic pointwise construction.
He uses Clavius's pointwise construction of the quadratrix as a counterexample. Descartes says that with the quadratrix, you can't just pick any point you want. The construction is limited by the fact that in Euclidean geometry, you can only divide arcs into powers of 2. So he's trying to distinguish between these two types of pointwise constructions based on how freely you can choose the points.
But here's the tricky part. Descartes claims that these generic pointwise constructions are basically the same as constructing a curve with continuous motion. But he doesn't actually prove this, which leaves us with this philosophical question. Did he really meet his own standards for what makes a curve geometric?
And then you have Paul Mancosu, who offers this interesting interpretation. He suggests that Descartes might have had a hidden agenda with his classification system. Mancosu thinks that Descartes' main goal might have been to exclude the curves that people had used to try to square the circle, specifically the spiral and the quadratrix, even if his stated rules don't perfectly match that goal. He points to Descartes' later writings, where he seems to say that he could conceive of the relationship between straight lines and circles in a clear and distinct way, which hints at a possible bias against those curves associated with this unsolvable problem.
If Mancosu is right, it means that Descartes' philosophical beliefs about which problems are solvable and what tools you can use might have had a bigger influence on his definition of geometric than this purely abstract idea of clear and distinct motions. It shows how intertwined mathematical practice and philosophical commitments can be.
And at the end of the day, as influential as it was, Descartes' program had its limits. Because he was so focused on finite algebraic equations and constructions based on clear and distinct motions, he basically ruled out the study of infinitesimals and curves that could only be represented by infinite series or more complicated expressions. And ironically, those were the very tools that Newton and Leibniz would use to develop calculus later in the century.
Yeah, but even with those limitations, what Descartes did was huge. He completely changed the game by creating this powerful and lasting connection between algebra and geometry. He gave us a new way to understand and solve geometry problems, and that framework is still relevant today.
Absolutely. And as philosophers, we need to remember that Descartes wasn't just interested in mathematical techniques. He was asking deep questions about the nature of mathematical objects and how we can have rigorous mathematical reasoning. His attempt to build this clear and distinct foundation for geometry reflects his whole philosophical project of searching for certainty and clarity in all areas of knowledge.
And that brings us to a final thought for you to ponder. How has our understanding of mathematical objects and proof changed since Descartes? Do his rules for what makes a curve geometrical still hold up in modern math? How do we define a legitimate mathematical object or construction method today? And what does all that mean for our philosophy of mathematics?
Really great questions to think about. We definitely encourage you to check out La Geometry and explore the history of early modern math. It's a deep dive that's full of surprises. Thanks for joining us.